Welcome back. It's basically Friday by our standards. Yay! Which means it's only one day from the assignment being due. A student asked me to do a quick demo of Handin, so we're going to start the class with that. First of all, Handin isn't a standard Unix command. It was actually made by and for people in this university. So it's only available on Aviary. If you try to hand in from your own machine, I don't know. No command found hand in? Oh no. So, first you just got to SSH into Aviary. And then go to the directory that contains your assignment directory. And of course, I did the assignment in order to make sure that I know what I'm talking about when I help you all. So I'll demo Handin by handing in my assignment. So at the bottom of the assignment outline, which is, of course, on the course webpage at this path, there's a command that you should use. So I'm going to do that too. Handin 2160, assignment 1. This much will be the same for everyone, but this last bit depends on the name of the folder you made for the assignment. So I just did A1, so I'm just going to do A1. I already submitted an assignment in order to test that Handin works. So, oh, you guys probably can't even see that. You'll get a slightly different message the first time you hand it in, but successive hand-ins will say, attempting resubmission of assignment, previous submission will be deleted. And that just means that when you hand in multiple times, it overwrites your submission, and me and the markers will have access to your most recent submission. It also means that you should totally hand in early and often, just in case your power goes out or you lose track of time and attempt to hand it in a minute past the due time. That way, you'll still have a relatively recent, probably worthy of some good marks, version of your assignment ready. So that's hopefully sufficient to explain how to use it. Yes? Good question. You should be outside so that that last bit of the command is able to find that folder within the current directory.
So it should be folder, that's the assignment folder in, right?
Yeah, I'll just use the document camera for this. I think you already understand it, but let's just make sure. A previous class or a previous instructor left all these papers here. So they're mine now. So you have your folder. That contains all your assignment 1 stuff. And that's contained within another folder, hopefully given a sensible title, like assignments. Assignments, of course, contains assignment 1. You should be in assignments when handing in assignment 1. And lastly, for the hand-in demo, I want to give a little bonus. Actually, I'm having second thoughts. I wanted to show off where the hand-in files are stored, like where all the assignment submissions are stored. And I'm mostly sure that you need a special staff permission to access them, but I didn't think to test that, and just in case you can't, or just in case any old student can access it if they know the path, well, one, that would be really bad security practice for the university, but just in case, I'm going to keep it a secret. Sorry for hyping it up and then going like, ooh, I'm not going to show you. So what's next? Right, before we get into the lecture, I was looking through the course material and found that pointers are never really given that good of an introduction. I talked a bunch about how pointers are memory addresses, much like arrays, and demonstrated why returning a pointer that points to local memory on a stack frame is dangerous. But there are a few more useful things to know about using pointers, and the course just doesn't seem to introduce them. So I'm going to write up a quick example live while explaining what I'm writing, and then upload that to the course website, and that'll serve as a sort of quick reference for pointers. So we're already in the Comp 2160 folder. I'm going to make directory pointers example, cd into it, then pointers.c to make and start editing a new file, I for insert, C boilerplate. You've seen all this before. You've seen all of this before. So I'm going to define a local variable and a pointer to that local variable. .64 is a cool number. And now int star pointer. What do we initialize it to? Well, one of the things that I'm aiming to show you for this example is that it's possible to get the memory address of any given value using some simple syntax. You just use ampersand, and then the thing that you want to get the memory address of. So on our infinite tape metaphor, every slot has a unique address. They're usually really long hexadecimal strings, but let's just count starting from 0 and not count high enough to make base 10 versus 16 matter. We have address 0, 1, 2, 3, and 4. A computer that can store 5 bytes of memory is dubiously useful, but we'll work with that. It's kind of relevant to my thesis, actually. I'm studying memory limitations. But anyway. Number is stored here, and pointer is stored here. What does pointer contain? Well, just a memory address. In this case, 0, in order to point to number. So this hopefully reminds you of objects and arrays in Java, and how when you pass an object around, you're actually passing a reference to that object rather than the object itself. C lets you control when you do that. And store pointer, which is very much like a reference to any value. So we're going to print out some stuff. %d placeholder for a number. And then to print a pointer, the memory address, you do %p. I'll explain this syntax in a moment. So we're printing out the number, the memory address that is stored in pointer, and then some third thing. This is another one of the things that didn't seem to be covered, but you pretty much need to know to effectively use pointers. Using the syntax star followed by the pointer gives you the value that is pointed to by that pointer. Return, yeah, it will still be nice here. Exit success. Probably include stdlib to get access to exit success. And this should produce some mildly exciting output. Cool, so we have our number, 64, pointer. This is what I meant by really long hexadecimal string. This is an address in the computer's memory. Evidently, number is stored at that address. And then by using star pointer, we got the value at that address. I'm just going to fix that print line to avoid that space after the new line. And this should be pretty expected, but if I modify the value of number, YY to copy a line and P to paste it. So if I do this, think for a moment about what should happen once we modify number in terms of what pointer points to and what's stored there. And as fast as it takes for me to talk and type, I'll show you what happens. We changed number to 128, and since pointer is just pointing to the memory location of number, it too changes to 128. And notice how the memory address doesn't change. The specific value here is mostly unimportant, but you will very likely run into a situation where you're not sure whether two pointers point to the same thing. So in that case, it's helpful to be able to see these and verify that they point to the same location. So I guess what I'm saying is exact values don't matter, but it's useful to compare values. One more thing I wanted to show off is that you can reassign pointers. Actually, before that, you can reassign what the pointer points to. So this time we modified the value by not accessing number, but saying that the value that pointer points to should change. And because pointer points to number, that value changed too. And what I was talking about earlier is that pointers can be reassigned. This is a silly example, probably equivalent to doing some weird array indexing. Oh no, reassigning isn't equivalent, ignore that. This is a weird example because you'll almost never add literal values to pointers. If you want to get something at a certain offset to a pointer, that's what array indexing is for. But it is often useful to make it so a certain pointer now points to a different memory location. Say you're looping through a list of not quite objects and you want to have a reference to the current one, like a for each loop, you do that. So when I copy that printing line one more time, I honestly have no clue what pointer's going to point to because we didn't specify what should be around this space in memory. So it'll likely point to some garbage. Actually, I bet it'll be 0. We'll see. Yeah, it's 0. Notice that the address changed, but by a little more than 1. Hope you're all familiar with hexadecimal. This means that it went 8, 9, A, B, C. And that's because when you add to pointers, it does a little convenience stuff for you behind the scenes, very rare in C. And instead of changing the pointer to point to 1 byte later, 1 slot, it changes it based on the type that it's pointing to. So in this case, int is 4 bytes. That's probably 32 bits. Yeah. So by doing pointer plus equals 1, we didn't actually say move pointer to the side by 1 bit. We said move pointer to the side by 1 int size. Back in the day, I didn't know this, and I tried doing like pointer plus equals size of int and couldn't understand why suddenly pointer was moving 4 or 8 spaces at a time. I guess I did have use for just moving a pointer directly. Whatever. This is some stuff you should know, basically. I'm now going to write some comments, which will have the dual use of reviewing what we just looked at, and then get on with the lecture. So we used AND to get the memory location, which is the exact same thing as a pointer. I'm going to fix up my grammar a bit. Cool. Reassigning the thing that the pointer points to. I guess I'm not sure how to end this sentence because it just reassigns a thing that the pointer points to. I guess I should say, observe that changes in the pointed to value follow through when you print the value the pointer is pointing to. Oh, and of course, access the value that the pointer points to using star. And you can use that star notation to reassign the value that it's pointed to. And you can do arithmetic on pointers. Long sentence, sorry. Bada bing, bada boom. So of course I recommend typing along with all examples because it sort of gets you to engage with it more than simply reading and listening. But if I ever get too far ahead of you for any reason, all examples like these will be posted on the course website. Cool.
Question actually?
Yeah.
Just I guess a clarification then. So like when we use star, like because we assign star pointer to the memory location of number, they're like basically, are they like basically always going to return the same value until we move the location of the pointer later?
Yeah, like star pointer is basically the exact same thing as number in that example. I'm not sure if that answers your question, but
It does.
okay, cool. And of course, when you reassign the pointer, then the connection is lost. It points to something else. And that is going to be a major pain in the butt once we learn about dynamic memory allocation, but that's a later thing. Today, should be able to, yeah, I hope you can type Clang by this point. We're going to talk about the compiler today, as well as interfaces and implementation. So all the compiler stuff is most useful for diagnosing compiler errors across C and other languages. I mentioned that this came in handy during a work term, but couldn't remember the context. I remember. It was my first work term working with Python, and spoiler alert to all Python enjoyers, most popular Python library code just links to C. They just provide a convenient Python interface for a C implementation, which works really well most of the time. Python is a much easier language to work with than C, so you kind of get the best of both worlds. But if those implementations break, such as if Apple Silicon Macs, i.e. Macs that use the ARM architecture, just came out and your work laptop happens to be one of those and no one has updated anything for ARM yet, then it kind of becomes a problem. So this will help most notably with situations like these, but also in general. And then interface and implementation stuff, that's pretty exciting because So far in the course, I've kind of just been showing you all what not to do, goofing off with illegal array indices and causing buffer overflows. This stuff basically turns the course into pre-software engineering. This stuff is foundational to what you'll do in the software engineering course and in any software engineering job in the real world. Oh yeah, and we're going to learn about structs. Structs are like objects, except simpler. And like most of C, they are simple in ways that cause problems. And hiding implementation details. We'll find out why that's important later. So, yeah?
I was curious, what language do they use in the software engineering course that you have?
Ooh, when I took it, it was Java. We made an Android app using Google's standard development tools, but that may have changed since I took it in 2021. Yeah?
It's still the same.
Cool. It's probably not going to change for like another 20 years. Welcome back, anyone watching the recording. At some point during the previous recording, my microphone died, so apologies for whatever audio you missed, as well as what's likely to be lowered audio quality for the rest of the lecture. I'll make sure to charge it before the next one. So yeah, let's talk about compiling. Java-C and Python has several compilation stages. C has 4, and also we don't care about how Java-C and Python work. This is interface versus implementation added again. Java-C and Python have effectively hidden the details about how they actually work, so you don't need to use those details, or don't need to know those details to effectively use them. Excuse me. C isn't as good at this. So its 4 stages of compilation are the preprocessor, code generator, assembler, and linker. I'm going to go through those one by one and show you all what input and output they have. Oh yeah, and you need to know a bit about how it works. Preprocessor. It's literally just a text replacement engine. Just does an automated find and replace on certain parts of your code. So it finds lines that start with the hashtag, such as hashtag include or hashtag define, and there are a bunch more hashtags out there known as preprocessor directives. So include literally replaces those lines with the files that you're including. Include is literally include. And then defines something that's closer to classical find and replace. And you can run just the preprocessor with Clang E. I know I just recommended coding along in the previous example, but this is probably the least important example ever to code along to. I'm just going to write a hello world program really slowly. Code along with all the other examples in this course, but for this one, the stuff on the slides about what each stage does and how to use it are much more important. So I'm actually going to skip part of the standard C boilerplate. You don't actually need to include any files to get a functioning C program. I'm just going to skip to int main void. And I can't do much now with this program. I guess I'm just going to define one variable. I can't return exit success because we haven't included stdlib, so I'm just going to return 0. Oops. And yeah, that's a minimal C program. So now I'm going to run the preprocessor on this. And it's actually going to do nothing, because there's nothing worth preprocessing. Or no, I guess there was some stuff worth preprocessing. It added a bunch of these tags to the code, which are referred to by later stages of the compilation process. So let's make our program a little bit more interesting and document it. Wow. And while we're at it, I'm going to define a useless array. Whose size uses a constant. And we'll define that constant using a hashtag define. So this gives the preprocessor a bit more to do. we see from the output that it removed our comments. I'm sure you learned, like, first class of first year, that comments are ignored by the compiler. You can see that in action now. And then we defined useless array as being as large as array size, and the preprocessor went ahead and replaced all instances of array size with its value. This next step is going to be kind of weird. I'm tired of just defining useless variables, and I want to actually print some stuff. And to print some stuff, I need stdio.h. So the output of the preprocessor here is going to look a little weird because stdio.h is going to be straight up copied and pasted into this file. And because that'll result in massive output onto my terminal, onto standard out, I'm going to use good old input redirection to pipe this into the pager less. Yeah, way more of those tags. And now we can get a glimpse into the source code for like the C standard library implementation. Seemingly giving more convenient or precise names to a lot of types. Cool, cool. There's totally a pointer to stdin somewhere here. I want to find it. Oh, also, we use file pointers sometimes. This thing is what it's pointing to. Nah. I'm just going to search stdin. Huh. Oh, searching for just pointers is going to take way too long. Let's ignore that. So stdio.h goes on and on and on. Oh, hey, printf. Cool. So I'm going to press capital G to skip to the end of the file. And look, it's our program. So part of the compilation process is taking all the files that are included within another file and turning them into one huge file. That's all for the preprocessor. The code generator takes output from the preprocessor and turns it into an abstract syntax tree. You don't need to know about this. You don't need to know about this for any point of your degree. I wish we had a compilers course. And then it translates that abstract syntax tree to assembly, which is instructions that are specific to your processor. At this point, the code is no longer portable and will not run on another computer with a different, certainly a different processor architecture, like x86 versus ARM, but don't quote me on this, maybe even different processors within the same family, like a Intel Core i5 of a certain generation versus i7. It's still text-based, but the great thing about assembly is that it can be directly translated into binary. Every single instruction in an assembly program corresponds to a specific arrangement of ones and zeros. And you can run the preprocessor and the code generator with Clang S. So let's go back to our program and Clang S it. Was that uppercase or lowercase? Uppercase. And I don't know why this is, but the preprocessor outputs to standard output, while the code generator and all further stages output to a file. So now we have a .s file for assembly. Cool. This is assembly, which is directly translatable to binary code, which means that the actual straight up ones and zeros that the computer is running as its program, it just does all this stuff. This is completely incomprehensible, but maybe not completely. I see push, that probably works with stack frames. Ret return, I'm not going to pretend to understand assembly. But hey, look, it's our string. And some metadata about the program. Notice that this is really short. You would think that the assembly corresponding to that massive program we generated by including stdio would have huge assembly, but it optimizes the abstract syntax tree. The compiler is smart enough to know that we aren't going to use the vast majority of the contents of stdio.h, so it's able to exclude those when creating the assembly. Up next is the assembler, which takes output from the code generator and does that like perfect translation to assembly. No, to binary that I mentioned. The result of this is an object file, which has very little to do with objects in object-oriented programming. I say very little because once we get into multi-file projects in this course, we're going to have object files for certain structs that we make, which corresponds to different files for different classes in Java, so they're pretty similar. Object files can't be executed yet because not all functions are defined yet. Our assembly here doesn't actually know what printf is. I guess we call it here, but it's never defined. The definition of printf lies somewhere within the operating system's code, and we don't know how to access it yet. That'll be the fourth step. So you can run the preprocessor, code generator, and assembler with Clang lowercase c. So let's do that. Outputs a file, a .o file. Yeah. Wow. Remember when I accidentally overwrote a .c file with its own compilation? Similar output here. Most of this is completely incomprehensible, but we can see our string here. Like, chars are just numbers, and binary stores numbers, so our string is actually still visible here. There is a hex viewer called XXD that we can use. This is beyond the scope of this course, though. And this just shows the precise hexadecimal translation of our program's binary code. Looks like our string is stored somewhere here. Wait, is I69? I didn't mean to make that joke. Oh well. So the linker, this part specifically, was the bane of my existence in that first work term. So it takes output from the assembler, i.e. the object file, and then it links the object file with function implementations. Right now, that just means take the binary code and put in, I don't know, the address on your hard drive of the printf implementation. But later in the course, we're going to talk about hiding the implementation of your own stuff so that other developers, perhaps on your team, can use your code without having to know exactly how it works. So the linker is going to come into use here as well. Implementations are platform and OS specific. Printf on Aviary is going to work differently from printf locally on my Mac, which will work different from printf on any Windows machines. And then it produces a file that is finally executable. And you can run preprocessor, code generator, assembler, and linker. That is all of the steps with just Clang. Clang is just these 4 steps, so yeah, if you want to run all 4, just run the normal command. Ta-da! I don't know why it doesn't do something like compilation.out, but whatever. Woohoo! We did it. We compiled a program. So that stuff isn't immediately applicable, but eventually you're going to be working with multiple files, and the linker is going to get mad at you because you didn't get your #include statements just on point. So you'll likely have to refer to these slides at one point. The next thing to do is an example that we're going to be referring to throughout the course. Well, I shouldn't say that. Throughout the next few lectures, we're going to take a deep-ish dive into an imitation of object-oriented program in C. Why are we doing this? To get really familiar with object-oriented programming, I guess? No, that's a bad justification. Along the way for this object we're creating, we're going to implement several good programming practices. Because, like I mentioned earlier, the course so far has been me showing you what not to do. Going into the real world with the knowledge that buffer overflows are dangerous is kind of useful. But starting from here, you're actually going to learn some good programming practices through this object example. So first, just a review of objects. Took kind of a weird path through Java. So start with primitives, and then explain that strings are like primitives but different. Then you learn about arrays and parallel arrays. And then classes and objects. So I guess we're going to have taken a similar path through C, but it is kind of an objectively weird way to study Java. It's an intuitive way for sure, because it goes from simplest to most complicated, but really Java is built on classes, and then stuff like primitives and strings are the implementation details. Whatever, let's move on. We're going to talk about structs a lot. The formal definition of struct is just a related grouping of related heterogeneous data. So that's different data, where an array could be homogeneous. And in practice, it's a bunch of variables smushed together, like a mini object. Notably, structs have no behaviors associated with them. Across programming, functions are like a reusable collection of code that is not connected to an object, while a method is a function that's connected to a class. C has no methods. not even an equivalent to struct. So here's an example of one. Say we want to represent a number in scientific notation. Maybe we're doing some scientific computing. Perhaps we're making a Python library that's made for scientific computing, and we need to run it. We need to write it in C for the sake of speed, so that people who use it can use Python for the sake of convenience without it being super slowed down, because Python's super slow. But anyway, the notation or the syntax should be pretty simple. You just have struct, the struct's name, curly brackets, and then each variable, laid out very similarly to the local variables of a function. And there's a semicolon. You will almost certainly forget to include the semicolon because it's a rare instance of semicolons having to follow curly brackets. So be wary of that. Get, set? Do you have like public and private and stuff? No. C doesn't have methods on struct, and no access modifiers either. Nuh-uh. Everything is basically public. There's no hiding of information. We'll have to implement that ourselves. So let's start to build our own data type. We're going to take all these stuff, the horrible, horrible stuff we learned about strings earlier in the course, and build up our hubris, say, yeah, I can do better than the C developers, and build our own string type. So first we're going to define the string struct, then we'll write a main method that populates it, and write some functions to replicate string methods from Java. Let's check out some Java documentation. This is also irrelevant. Java has a ton of methods for strings. So we're going to implement a very small subset of them. So let's get coding. I have so many string examples. Let's call this the string class example, because we're using C to replicate classes in order to better learn about classes and their pitfalls in the real world, blah, blah, blah. Okay, now you should start coding along again. So let's make a struct. It's customary, most common convention to write struct types in all caps, but there's another convention on top of that that makes naming them a bit simpler. I'm going to go through this convention of using all caps names, show you why it's inconvenient, and then use the more convenient naming later, which will also explain, sort of give a justification for why they're all caps right now. For now, just bear with me. Open bracket. We're going to store a C string. And how big should it be? Well, this will kind of remove our ability to manage the memory associated with a string from the program using a string. So we need to decide that right now. Let's make a constant and define it up above. Hello? Okay. I was just repeatedly trying to use capital O to insert above the current line. $500. We're basically going to hope that each string is less than 500 characters, and perhaps later we can implement some sort of system for warning the user if they're about to exceed the size limit, or maybe make the array resizable by allocating memory differently and pointing to a different memory address. Or we might just write in the documentation that strings are a maximum of 500 characters long, 499 if you don't count the null terminator, and hope that people read the documentation. That's the worst option. Nobody reads documentation. Oh, forgot a semicolon. I can press U to undo my latest action in Vim. Capital A to insert at the side, or at the end of the line, and semicolon. First of many convenience features, our string is going to know its own length. Yay! And then closing bracket and the all-important semicolon. Let's make a main function that uses our new struct. And now we're going to get into that naming issue that I alluded to earlier. Our struct is a type, just like the classes you made in Java. And you'd think that you could just do string, my string, something like that. That won't work. The compiler will get mad at you. I'm going to keep it here, though, so we can see the specific error message. And then this main method will use functions that we're yet to define. Grammar is, though. Ooh, printf. I'm going to have to include stdio. I type lowercase g twice to go to the top of the file, uppercase O to insert above the current line, and include stdio.h. Nice. And now we want to print out the contents of the string. And the notation for doing that is very similar to accessing properties of an object in Java, or Python, or C#, or even C++. Dot. Now, this might seem kind of antithetical to what we're doing. The fact that we can just access mystring.contents willy-nilly and then perhaps do as much buffer overflowing as we want. That is a problem right now, but it won't be a problem forever. Eventually, we'll be able to hide the contents of struct string in a way that contains a useful software engineering lesson. Ooh. Let's attempt to compile this. Minimally, it's going to have the linker complain about missing definitions of make string. And hopefully it'll also complain about me fumbling the type name. And there are probably some syntax errors in this too that I made accidentally. So we'll catch those along the way. Also, I named the file string and not strings because I'm basically following the convention of naming a file after the type that it contains, and naming types with singular nouns because they're just one thing. Having a main method in string.c is kind of weird, but that's another thing that we're going to sort of extract out later, and that you will extract out of a stack ADT in the second assignment. I guess I never went over what an ADT is. If it doesn't show up on Monday's lecture, I'll make another tangent like I did with pointers. Okay, first error is the one we wanted. Must use struct tag to refer to type string. I don't know why this is, but the glorious, infallible C developers, probably in the 1970s or so, decided that in order to refer to structs, you need to type struct and then the type of the struct. This was probably to reduce ambiguity with other built-in types, possibly to avoid some wacky logic in the compiler. That it was a memory limitations thing. But now it's kind of just a historic thing that we do for historic reasons. Now, what's happening here? Implicit declaration, yep. And then assignment to struct string from incompatible type int. That's really weird. I'm going to see if makeString is a built-in library function, because this problem has different explanations based on whether the C developers actually made a makeString function on their own. Okay, probably not a built-in function. We're just going to make a little bit more sure by renaming the function into something that hopefully no one making a thing worth using will ever name a function with. Invalid suffix on integer constant. Where does that U start? Oh, I put a semicolon in the key smash? Neat. Okay, so now the compiler thinks that I just assigned my string to the value of some uninitialized int variable, well, uninitialized variable that it assumed was an int, called makeString whatever, with the suffix of this. Getting more distracted by the second. We'll get back into programming practices soon. Okay, same errors. Nice. I was afraid of talking out of my ass about a function that exists and I have no ideas of the details of, but it looks like this is what I expected at first. The linker can't find a definition of the function makeString. So I'm going to try, oh no, I can't try running the program, we got errors. It first did a sort of contingency of assuming that our makeString whatever function is a function that returns an int. That's kind of interesting, probably implementation dependent. And a similar idea to an uninitialized variable just being whatever memory it happens to be in there at the moment, which is also implementation dependent. Actually, I think this is part of the C specification where if you don't specify a return type, it defaults to int, but that's not important because you should always specify your return type. Let's get back to business. I'm going to delete until the end of the current word by pressing D for delete, W for word. And let's start making functions. We need to forward declare them. Oh yeah, I gotta fix this error too. There is a way to avoid saying struct type every time. Yeah, let's just implement it now. This is sort of secondary, never required, but you're probably going to want to do this on the second and I think the third assignment uses structs. You're probably going to want to do this on the assignment to save yourself some typing. We use typedef to give an alias of a type that we can use in place of that type name. Like that. So now, from now on, we can say all lowercase string. Actually, I'm going to change that to title case. That's a bit more consistent with what we've typed in the past when making objects. So now instead of struct string, you can say string. And this should just work. Let me just check my syntax. Cool. It's just freaking out about makeString. Oh, and look, our error about the incompatible types acknowledges our new name and gives you a helpful little message about what the name is referring to. As an aside, this has a decent amount of applications for making your code more readable. Like, say you're writing a program that keeps track of the number of students in a class, and the number of students can go to 0, but not below that, and it can be any positive number. You can say typedef unsigned int number of students, and then use the type number of students whenever you use an int. That example is kind of janky. You should probably just use int, but you can hopefully see how it might be useful to relabel a type in order to give whoever's reading the code some information on how it's used. For now, though, we're just going to use typedef to avoid some typing, as in keyboard, not as in type system. Avoid typing when referring to our struct. We're definitely not going to finish the implementation of this structure in this lecture, but that's okay. This example is supposed to be spread out across a few classes as we sort of, I think, alternate between writing the code and explaining what we're doing. It's supposed to be like that anyway. So before you leave, I'll make the prototypes and just get barely started on those function definitions. Also, I accidentally used a term I hadn't used before. I said prototype to refer to this declaration of a function. That's just another term that you might see in the wild. Another name for this, for a declaration, is prototype. I don't know why that word is used, but it might be referring to the signature of a function as a type. I don't know. Notice this parameter, string self. We are imitating what object-oriented languages do to call methods. Python does this explicitly, has a self parameter as the first parameter of any method. But actually, every single object-oriented language does this implicitly. Methods are just functions that take an object. Cool. So I guess I lied about methods not being in C. We're about to make a method. Still no objects, though. And then, let me just copy these lines. Capital V to go into visual line mode. Select the rest. Y to yank. P to paste. And then capital A to insert at the end of the line. Making all the changes that we'll need to make to turn it from a prototype to a function implementation. Oops. And we're done for today. So assignment is due tomorrow. Hope you're all having lots and lots of fun with it. I will be answering emails about it on Friday. And show of hands, would anyone find it useful for me to have like office hours all day Friday to drop in and get assignment help? Just one, maybe? Oh, 2, 3, 4, 5. Okay. Do you have a meeting this Friday? Let's say I'll be in my office for noon till 2 o'clock. Yeah, sorry, maybe that was a bad offer to make because I'm kind of busy. But anyway, my office is E2464. Drop in if you want in-person help, and I'll be answering emails too. Also, I just implicitly revealed I have my office. So an announcement of my office hours will come as soon as I decide my office hours to avoid conflicts with other instructors in other courses. But yeah, that's coming soon. Good luck on the assignment. Happy Friday equivalent, and I'll see you all on Friday or Monday.